Okay, so seems like we're live at this point. Hello, everybody. My name is Alex Forensich. I am a postdoc at UC San Diego, and I've been working with FPGAs for a number of years. And today I'm going to do some porting and unboxing in relation to a couple of new boards that I just got in from Xilinx. I've got a U50 and a U280 here. So I'm going to go ahead and unbox those in a couple of minutes. We'll take a look at the cards. They should be kind of interesting to look at. And then I will pop one of those in a dev machine and we'll see if we can get Corundum running on it. So just a little bit of background on the on Corundum. It's an open source NIC, and the idea is that it can be used by research groups or whoever really to experiment with new NIC features. So I'll talk about that more in a few minutes. But first, let's take a look at these FPGA boards, and we'll see what they look like. All right. Hopefully, all of this works here. So I've realized one thing about why these boards are so expensive. Xilinx has spent a great deal of money in the marketing and graphics design department. I don't know if you've seen the boxes that most GPUs come in, but the boxes that these FPGA boards come in are just absolutely amazing. So there is the U50 in the box. All right, AU280, and then we also have a U280. Aren't these boxes just absolutely amazing? Yeah, we got the nice Xilinx logo on there. Oh yeah, very nice printing quality. Okay, so both of these cards are data center grade, intended for installation in data center environments. So yeah, I don't think they spent very much money on the boxes. Anyway, we'll start with the U50 and see what that looks like. Okay, so there's not much inside the box. We have just some documentation, third-party copyright notices and licenses. Not particularly important. And then we have the card itself inside of a nice anti-static bag. And let's see what kind of accessories they provide with that. I'm hoping a JTAG cable. Probably not, though. That is a PCI Express bracket of the other size. So this is a short one, and the card includes a long one. Not much in terms of accessories. And the interesting thing is they don't even include a Vivado license with this card. So if you're going to get a U50, then you're probably also going to have to get a license. The U280 might include one. We'll take a look at that in a sec. Okay. Let's see here. Get into this bag. All right. Okay, so this is one of the Alveo U50 boards, as it says right on the tin. Nice red color. I like that. Brushed aluminum. So the FPGA on there, you can see maybe is rather large, and there's not much else on the board aside from the FPGA and power supply components and the QSFP 28 module here. And then the card has a PCI Express edge connector here. Now the heatsink on this card is actually kind of an interesting design. Most of the heatsinks that I've seen, the fins are parallel and they run the entire length of the card. But on this one, they're kind of fanned out. They start out close together at the back, and then the fins end periodically along the top of the card. So some of the air going in the back comes out the top, actually. So I'm not sure what that does in terms of cooling. The other thing interesting is that the heatsink here is actually painted black. Not sure what that does to the thermal performance. So in terms of the I/O that this card provides, there is the PCI Express Edge connector here, and that can be run, well, by default it runs in Gen 3 by 16 mode, so you get about 128 gigabits per second. But the chip on here is one of the newer HBM parts that supports operation at PCI Express Gen 4. And when we're running at Gen 4, it only supports 8 lanes, but it's actually possible to bifurcate the interface into 2 groups. I got a question, are the Alveo cards supported under Webpack? I'm not sure, actually. I would have to look into that. I think if you're going through Vivado, you might need a license. I'm not 100% sure. Anyway, let's see. So to get code onto this card, if you're using the Alveo environment and you're using the Alveo shell, I believe that's done over PCI Express. But if you want to do away with the Alveo shell, then you have to use JTAG, and the JTAG interface that this card provides is this little 30-pin maintenance connector here, which is highly annoying because this seems to be the only card that has this maintenance connector on it. And you need to get a cable that is specific to the U280 in order to actually load code on this card. I don't have one of those yet. I did actually order some samples of the corresponding cable from Samtech. They're actually really good about that. I think I ordered the samples like yesterday or the day before, and they just showed up today. So free samples and overnight shipping with a university email address. So that's pretty good service. So yeah, if I don't get the cables, then I'll probably use this to try and figure out what the JTAG pins are on that cable so I can use it with one of the platform cables that I already have. Anyway, what else is on this card? We also have the QSFP 28 connector. And for those of you not familiar, the QSFP 28 is a connector that supports 4 parallel connections of up to 25 gigabits per second each. Actually, the QSFP 28 is capable of 28 gigabits per second each. I'm not sure what protocols actually run at 28 gigabits per second, because I'm mostly familiar with Ethernet, and that runs at either 10G or 25G per lane. So I can show you some QSFP 28 hardware a little bit later. Let's pull out the U280 and then we'll take a look at that. So the U280, they said, similarly comes in the most boring box ever. We do have a Xilinx logo on there, but that's about it. So let's take a look at what we got in here. Okay, so this one actually comes with a voucher. So there's a code on here. I'm not going to show it on the stream, but yeah. So this one can be used to get a single computer license for Vivado for targeting these devices. And then there's also some additional paperwork in here. I think that's the same kind of thing, just legal stuff. Safety instructions. Really? How dangerous are these cards anyway? Okay. Let's see what we got in here. Got nice little alignment pegs in the corners of the foam. Does make it a little hard to get out. Anyway, here's the card. The Xilinx Alveo U280. And this thing is rather dense. It has a very large heatsink in there. So we'll take a look at that in a second. Let's see what else is in the box. All right. If I can do this without taking out my camera setup, that would be good. Okay. We got not much, just a USB cable. Well, that's a step up from the U280. let's get that box out of the way. And my camera just decided to turn off. What's up with that? Okay, there we go. All right, so here we go. We have the U280 in the bag. Let me go ahead and get this out of here. All right, so this card is a bit of a beast. It's basically in a GPU form factor. Now I got the active cooled card, so this has a big blower fan at the back, but they actually make two versions of this particular style of card. One of them with the fan, and one of them without the fan. So this one is better for installation in like in a desktop computer, but if you wanted to install it in a server, you can't put two of these cards next to each other because they would block the airflow. So with the passively cooled card, they just the back of the card is just open, and it's reliant on the fans that are already in the server chassis to get sufficient airflow through the heatsink in the card. So this card, it has PCI Express Gen 3 by 16. Well, I guess this one also supports Gen 4 because it's also an HBM part. Except you can't do Gen 4 by 16. You can only do 2 Gen 4 by 8s if you want to use the whole edge connector. The FPGA on here has 2 HBM stacks of 4 gigabytes each, and then it also has a pair of DDR4 memory modules. So some of the other Alveo boards, they'll have 4 DDR memory modules. So with this one, it's a little bit of a trade-off. You get less DDR and a little bit less memory capacity, but you do have the HBM, which is a much higher bandwidth. And then on the back of the card, it's also pretty Spartan. We just have a pair of QSFP connections. On this card, however, unlike the Alveo, or unlike the U50, we actually have a USB connector on the back, and this goes to an on-card JTAG setup. So it's actually possible to plug into this card with just a USB cable and load custom designs on it. I think there's actually one other difference between the active and passive versions besides the presence of the fan, and that's the location of this power connector. In a server chassis, in some cases, you don't have much room on top of the card. So what they do on the passive version is they actually move that connector to the back. And if you look right behind where the fan connector is, there's a couple of large unused copper pads, which would correspond to the other location for this connector. All right. So let's see. I can give you a real brief overview of QSFP connectors for people that are not familiar. This is what a QSFP28 direct attach cable looks like. These are the actual QSFP connectors. The actual connector is just a board edge connector inside, and then they have this metal casing around the outside. So these are inserted into the back of the card like so, and they clip in there with a nice positive retention, and you have to pull on this tab to get it out. Pretty straightforward. So these are capable of giving you 4 bidirectional serial links. So there's eight pairs going through here, and with a 2-meter cable, you can tell that that's a pretty thick cable. If you want to go longer distance, the cables get even thicker. So for short connections, these are cheap, but not very nice to use mechanically. What these connectors are really designed for is to accept optical modules. So this is a 100 gig optical module, a let's see, QSFP 28 IR 400 gig. So this is a 1310 nanometer module that's capable of forming a link up to about 2 kilometers or so. So for a lot of applications, that'll get the job done. So this installs in the card exactly the same way. But then instead of providing a connection through a fixed electrical cable, it has an optical connection here. So you can see there's two slots in there, each one to accept a single fiber. So this is what's called a CWDM module. So it actually uses 4 different wavelengths of light to carry the 4 parallel channels. So inside of this module, there will be 4 lasers, 4 photodetectors, and some optics to multiplex and demultiplex those 4 devices into each one of these fibers. So these are called LC connectors, and this is what the mating connector looks like. In some cases, you'll actually get cables that have 2 of these bound together. This is all I have at the moment. So, yeah. I also have a 100 gig NIC, and this is one of the Mellanox ConnectX 4 devices. So we're actually going to be using one of these at the other end of the link to test the Corundum design on the card. So yeah, as you can see, this is much smaller than the FPGA board, but then this doesn't have any RAM or anything else. This just has the NIC ASIC on there from Mellanox. Another type of cable you can hook into a QSFP connector is what's called an active optical cable. And as you can see, this is very similar to this optical module, except the fiber is permanently attached. And these are good for, you know, medium range connections where you don't need to go through patch panels and things like that, because they are more expensive than direct attached copper cables. And you have these optical modules permanently attached to the ends. But the flip side is they are cheaper than, in most cases, than getting this type of module, because they can use, well, they have full control over the link budget. They don't have to deal with, you know, some unknown number of connectors and whatnot. And they can make a reliable link by just directly connecting the fiber on both ends. So this connector, or this fiber here, is blue, indicating that it's probably a multi-mode fiber. So even though this module doesn't say on it, it's probably a good assumption that it's operating at 850 nanometers. All right, so let's go ahead and get this card installed in a computer, and then we'll see if we can get Corundum running on it. Let me get this out of the way, and I'll grab my dev machine and install the card. Okay, so this is one of the 2 AMD machines that we put together. So we don't necessarily need an AMD machine, but this is the only machine that I have access to that's capable of taking this card at the moment. All the other machines are inaccessible in machine rooms on campus. So this will have to suffice for now. All right. Let's see here. The hard part is getting this thing aligned in the PCIe slot. There we go. That is a massive card, all right. Okay, so we need to get this thing screwed in, and then power hooked up, and then let me see if I have a USB cable here. All right, there's power. And one nice thing about some of these server motherboards is they actually give you a normal USB connector on the motherboard. I'm not quite sure what that's used for, but it's very convenient for running an FPGA board like this. Let's see if I can get this connector in here the right way. Ah, there we go. Okay. So I think this will be sufficient for testing. All right, I'll go ahead and get this thing powered up, and we'll see if we can talk to the card. They do put quite a fan in those cards. I'm not sure if you heard that spin up, but fortunately it spins down pretty quick. Presumably they have one of those fan management chips in there that can monitor the die temperature. Somebody asked if there's P4 support on Corundum. Not currently, but well, basically the idea behind Corundum is that it provides the host interface. So you can add whatever arbitrary processing or packet processing logic you want outside of that. We'd certainly be open to adding support for some sort of P4-based packet processing system. We don't have specific plans at this point in time. But yeah, it's absolutely possible to cut it right between the kind of the core logic of Corundum and the optical modules and the Mac modules, and insert whatever you want. And I think there are some existing P4 projects that you could probably just drop right in. Now, in terms of the software integration side of things, I don't know. We'd have to revisit that and see if we can get something working. But I am open to doing that if there's other people interested and willing to help out. All right, let's see. I think that machine is booted up. Let's see if we can connect to it. Okay. Although it doesn't make that much difference because we're probably gonna have to reboot it a couple times in the process of getting everything set up here. I guess it's not done booting yet. Well, the nice thing is it's a super micro motherboard. Let's see here. Is that the right address? Might not be. Yeah, that might be right. Really? All right, I'll have to deal with that later. Let's see if this boots up. Oh, that should be, yeah, that is right. Okay. Why does it not like my password? Well, it's always something, right? I got that card seated in there properly. Whoops, looks like I had the network cable plugged into the wrong port. Let's see if this will figure itself out now. Well, I'll take a look at that later. For the time being, let's see if we can get the Corundum design built for that board. Without doing that, then there's not really much point in trying it on the hardware. Okay, so let's see. We're going to start with the VCU 1525 design because the board is very similar. It has a Vertex UltraScale plus FPGA. It has a similar PCI Express interface, and it has a pair of QSFP 28s. So what I'm going to do is make a copy of the VCU 1525 directory. Let's see. Okay, and then we'll see if we can get it running at 10G first. Okay, AU280, FPGA 10G. All right, so let's see what we got here. Corundum has really only two interfaces that are necessary for the design to do something useful. You have to get the PCI Express interface working and the Ethernet interface. Oh, let me actually clear out all this old 1525 stuff here. Okay. All right. So this is the part that's on the 1525. All of this is basically going to stay the same. Main thing, actually, let's see here. Okay, so let me just pull up the block diagram of Corundum real quick. Corundum is divided up into several different components. The FPGA and FPGA core files here are basically the top level of the design, and these contain all of the interface components. So the MAC and PHY components to interface with the SFP modules, or QSFP modules in this case, as well as the PCI Express modules to communicate with the host. There are a few other odds and ends, including some LEDs and switches and I2C interface and some QSFP module control pins. They're not necessarily for operation, but they are, well, so the QSFP pins here, the I2C interface on these boards, at least on the 1525, everything goes through the I2C interface. So the QSFP modules, they go through an I2C MUX, and then into the I2C here. Other boards have dedicated pins for the I2C interfaces on all the modules. But if you want to insert an optical module, then you actually have to basically turn the module on by driving the reset and lpmode pins appropriately. So on the 1525, those are directly connected to the FPGA, and you need to drive them correctly in order to turn the transceiver on. If you use a DAC cable, it's less of an issue, because a DAC cable literally has nothing in it besides just wires. Well, it also has like an ID EEPROM, but that's not really all that important. Anyhow, let's see here. So this is the setup for the 1525. The question now is what we have on the AU280. So let's pull up, let's see, the manual for the AU280. Which one is that? This one, I think? Right, here's the user guide. So let's see what's actually on this card. So here is the FPGA, and it has a bunch of stuff hooked up to this satellite controller, apparently. The annoying thing is it looks like all of the QSFP control pins are hooked up through port expanders, and they're only controlled over I2C from the satellite controller. It looks like the main FPGA actually has no connection at all to these QSFP modules. I don't know who the hell came up with the idea to design it that way, because that is incredibly annoying. I mean, it basically means that you can't talk to the transceivers at all and change any settings. And for what we're doing, at least in terms of research group, sometimes we have to do that. Well, I guess we'll have to revisit that later. Hopefully this at least pulls the lpmode pins so that the transceivers will turn on. As far as the PCI Express, that's going to be a direct connection. Let's see. 4x GTY? Oh, I guess they mean 4 quads, because there should be 16 channels going to the edge connector. And then there's going to be a ref clock as well, which I guess is not shown in this diagram. Okay. So we got PCI Express, RX and TX, E and N, 16 channels for each of those, and then we have the ref clock and the reset. And then for the QSFP modules, we have 4 transmit pairs and 4 receive pairs. And then some number of reference clocks. I think on the 1525, we just ran everything off of 1 ref clock. I guess we could probably do the same thing here. Okay. Let's see if we have a listing of all the pins. I think they obfuscate that. I don't think the manual will actually have much in terms of documentations here. Yeah, so they have how to get access to this in Vivado if you're going to use the board-based flow. Otherwise, we may have to dig up the XDC file. Now, so that's useful. They have some information on how to configure the design for loading out of flash. So this has all of the configuration parameters for the flash part. So it looks like they're using a 4-bit SPI interface, so single QSFP. Single QSPI, not a dual QSPI that you see on some boards. Alright. Oh, they actually have the transceiver connections here. So they have the pin numbers, and they have 2 different reference clocks for each one. So one of these is coming from an SI570, and the other one is coming from, well, something else. Let's see what this says about that. Or does it say much about that? Each QSFP connector has its own clock generator with 2 frequencies. See clocks for details. Alright, so there's 2 frequencies here. One is 156.25. That's a very standard reference clock for 10 gigabit Ethernet. And the other one is this 161.132, which is a really weird number, you might think. But these are actually all related to the line rates. So, just a quick side note here. You probably think 10 gigabit Ethernet, it probably runs at 10 gigabits per second, right? Well, it depends on how you measure it. 10 gigabit Ethernet is encoded with something called 6466 line code. that takes 64 bits and converts it to 66 bits. So if we do 66 over 64, we get about 3% overhead. So if you do that and you multiply that by 10, well, that's 10.3125, and that's the line rate for 10G. And for 25G, it's 25.78125. And for 100G, you run 4 of those in parallel. So for Ethernet, unlike some other protocols, the bit rate that's specified is before the line code, and the actual link is running a little bit faster. For many other protocols, the marketing guys took over, and it's the other way around. So for PCI Express, you might have heard that PCI Express Gen 1 is, say, 2.5 gigabits per lane. Well, PCI Express is 8B10B encoded, and those numbers are after the encoding. So if you take 2.5 times 8 over 10, you get 2. So it's actually 2 gigabits per second per lane. Same thing with Gen 2. Gen 3, they switched to a different encoding. It's 128, 130. So let's see, it's 8 gigabits per second per lane times 128 over 130, and you get about 7.9 gigabits per second per lane. So yeah. So getting back to Ethernet, the question is, where do these numbers come from? Well, 156.25, I think, is just 10G over 64. There we go. Yeah. So that's where that one comes from. And then the other one is, I think that's just 10.3125 over 64. There you go. Yeah. So either of these numbers can be used by the PLLs in the transceiver module to generate the line rate. And I think it's a little bit easier going from the 161 than from 156, at least if you're running at a 25G line rate. Because you need to multiply by, let's see, I don't feel like doing too much math right now. But that's where these numbers come from. They look really weird, but they are directly related to the actual line rate. And when you're running at 100 gigs, at least from previous experience, if you use the 156.25 megahertz clock, then when you set it up in the transceiver wizard in Vivado, you have to use a fractional divider to actually make that work at 25 gigs. If you use the 161, then you don't need to use a fractional divider. Now, I'm not sure if this really makes much difference from a practical perspective. In some cases, you're either stuck with using 156. I know a lot of Xilinx boards, like the VCU108 and VCU118, they have reference oscillators that out of the box run at 156. They're the SI570 If you want to change it, you can, but it's kind of a pain. You have to, it's not as simple as just writing a constant. You have to read out the current value in there and do some math, including a like a long division, and then write it back. And doing that in Verilog is not great. If you want to do it in a soft core, I guess you can, but the alternative is you just leave it at 156 and set the fractional divider. It's possible that if you do that, you get a little bit more jitter. I'm not sure how much of a difference that makes. All right, so let's see. Okay, so this now talks about all the clocking. So there's a bunch of clocks on the board that are intended to be used by various devices here. So they have, what is this, 2 clocks at 100 megahertz that are intended for use by the DDR4 memories. And they have an extra 100 megahertz clock that's just for whatever you want. And then they have a clock coming from the PCI Express Edge connector. And this one, they send it through a splitter, it looks like, a clock buffer, and then drive it to 2 different reference clocks, or 2 different reference clock inputs. And the reason you need that is if you want to use it in bifurcated by 8 mode, when you have 2 X8 interfaces, then each one of those needs to have its own reference clock. I'm actually not sure why that is. I think that's just kind of a limitation of how the Xilinx wizards and whatnot work. If you can do 16 lanes with one, then you should be able to do 2 sets of 8 lanes with one because they are the same transceivers. Let's see. Then there's another 100 megahertz oscillator that also supplies the PCI Express reference clocks. This looks like, okay, these are different sites. So this one is, so these two are ref clock 0, and these two are ref clock 1, presumably to the same transceiver site. Yeah, here we go. This is 225, that's also 225. This is 227, that's also 227. Right, so that makes sense. So then you can switch between whichever one you want depending on whether you have a signal from the host or not. Let's see, what else? Okay, so each QSFP quad has a couple of different reference clocks. There's QSFP 0 clock MGT ref clock 1 coming from a Silicon Labs part. And it looks like there's 2 additional pins that are associated with that. So there's an OE pin that's used to turn it on or off, and then a frequency select pin. It'll select either 161 or 156 depending on which way you tie it. Okay. And then we have the same setup for QSFP1, and then ref clock 0 comes from a different source, an SI570. The reprogramming I2C is only possible via the satellite controller. Right, so I have no idea how you would do that then, because I don't think they have anything documented about that satellite controller, which is kind of annoying. So it drives, let's see, this is just a general purpose input. Yeah, just regular I/O pins, and then 2 MGT sites, 134 and 135. Ref clock 0, which corresponds to these guys, right? This one is, this one, where are we doing? Where is this 0? Here's ref clock 1 on 135, and here's ref clock 1 on 134. So these numbers here indicate the MGT site. It's sort of similar to the I/O bank numbers. So when you have an I/O pin, this is a pin, technical pin name, super long. That's the actual pin, and I think that's the bank. So that's bank 75. And each bank you can tie to a different I/O voltage or whatever in terms of the normal I/O pins. The MGTs come in groups of 4, and each group is assigned a different number. So 134 will have 4 GTY channels and 2 reference oscillators, 2 reference clock inputs. And these are dedicated pins on the chip. You can't use those pins for anything else, even though you occasionally see people on the forum asking about, oh hey, can I use a PCI Express connector for, you know, regular 3.3 volt I/O? No, you can't. CML only. Let's see. Oh, they have a bunch of miscellaneous I/O. Oh, this document is actually a bit more comprehensive than I was expecting. So that's for talking to the management controller. So we have the I2C interfaces. Except this seems to be, this is a slave I2C data connection, so it seems like this is kind of useless because you can't talk to the board from the FPGA. This is just for the management controller to talk to the FPGA. Interesting. We have another couple other interesting pins here. This one, power broken, is that what it means? Active low input signaling PCI card shut down. Never heard of that pin before. Interesting. There's their PCI Express reset connection. Cat trip. HBM cat trip. Active high indicator to indicate that the HBM has exceeded its maximum allowable temperature. And then that, I guess, shuts off the power supplies. Okay. Well, we're not using the HBM for the moment, so we'll ignore that one. I'm not sure what that's for. Here's the SI570 and the other 100 megahertz clock inputs. Okay. So the main things that we need are the reference clocks for the QSFP modules and the connections for all the serial channels and the reference clock, PCIe reset, and PCIe connections. It looks like this board doesn't have any FPGA accessible LEDs on it. Now that would make it kind of a poor starting board. You want to do a blinky design or something, they don't even give you an LED to blink. Go figure. But let me pull up the XDC file. let's see, this is the Alveo U280 XDC. So this is what Xilinx provides for the part. Let's see what we can corroborate from here. So we've got, okay, so they have everything doubled up. One line for the pin, one line for the IO standard. So this file, if you're not super familiar with Vivado, the XDC file contains all of the constraints, either timing constraints or placement constraints. So in this case, this is all of the placement constraints for all of the pins. So in this case, sysclock 0 is connected to package pin BJ44 and BJ43, and it's an LVDS IO standard. Interesting that they have location parameters for both pins. Half the time whenever I try to assign both, it gives me a warning about one of them. Yeah, PG348 has the details of the satellite controller. All right, well, we'll take a look at that. And the CMS subsystem IP. All right, well, we can circle back to that later. It's not necessary to get the basic core data path operational. Well, unless it doesn't turn on the optical modules, in which case it could be kind of hosed. Anyway, we'll take this one step at a time. If it comes up over PCI Express and the driver can talk to it, that's a good start. That might be all we can accomplish today, if we can't access those pins on the transceivers. Okay, so we've got two system clock inputs. These are set up for the memory interfaces, right? That's what it says here for memory interfaces, 1.2 volt banks, 65 and 69. Okay, and then we have LVDS system clocks. Here's the other 100 megahertz clock and the SI570 clock. And then these are the PCI Express clock inputs. So we've got the 100 megahertz host clock, and this one is for Gen 3x16 for the upper 8 lanes of the, if you run it in bifurcated mode. And these are for the lower 8 lanes when running in bifurcated mode. So same thing here, we have, this will be coming not from the edge connector directly, but from not a clock mux, a clock buffer chip. There we go. And then these are coming from some other oscillator. That's just a fixed 100 megahertz oscillator. Okay, so we'll be using, I guess, this one, right? Yeah, because we're going to run Gen 3x16, so we need that. And then for the QSFP modules, we have the two modules here. Okay, here's OE bar, which is the output enable, and FS for the frequency select. And then we have the SI570 MGT clock, which is the 156.25 megahertz clock. And then we have the QSFP 0. Oh, this is the from the other Silicon Labs part, the selectable one, either 161 or 156. Okay, that's pretty straightforward. And then we have, oh, these are all the clock constraints indicating the frequency of all these inputs, 6.4 for 156 and 6.206 for 161. If you're wondering where those come from, well, get my calculator going again. Let's see here. So if we do 156.25, if we do 1 over that, you know, that's 6.4 nanoseconds. Okay, and then 1 over, well, let's see. No, other way around. That's 6.206 for 161. So that's where those numbers are coming from. There's nothing particularly weird about that once you understand where the frequency comes from in the first place. Okay, so here's the PCI Express reset line. And then I need to do some reading on this. I think we can probably ignore that. Sysmon, STL, and SDA, right? This is coming from the satellite controller. Xilinx has a lot of typos in this file, apparently. Oh, so here's a second. Oh, never mind. Okay, this is for the system monitor component on the FPGA. So this one is not really going to the FPGA logic, but this goes to the system monitor module, which is capable of monitoring, you know, the die temperature and the power supply voltages and whatnot. So I'm not even sure if it's necessary to have those in the XDC file. Anyway, these are the connections I2C from the satellite controller. We got USB. This one is to the FTDI part on the board. That goes to that USB connector for maintenance. So I guess that has both the JTAG connection and a USB serial, and here's the other end of that. And then we have the connection to the satellite controller. So I guess this is what Evan just mentioned. This will go to the satellite controller and talk to whatever firmware is running on there. Okay. Oh, CPU reset FPGA. Hey, we actually have a button connected. Wonder of wonders. Okay. So we don't have any LEDs, but we have a button. Go figure. And it's designed to be active low. Okay, fair enough. All right, so let's take a look at the XDC file and see what we can actually keep and what needs to be updated. So let's see, general configuration, I'll leave that alone. We have all of the DDR clocks. So the 1525 has 4 DDR modules, and each one has a dedicated 300 megahertz clock input. So what we're going to do is, well, actually, is that important? That's not very important. I'm going to skip these for now. I'll clean this file up later. The priority for now is to get the main stuff we need for Corundum operational. So if I don't need it, I'm going to ignore it for the time being. So LEDs, there are no LEDs on this board. Well, we're not even using the reset connection. I don't think there's an accessible dip switch. I didn't see one anyway. And there's the UART connections, which we're not going to use. And then the QSFP 28 ones. I comment all these out, make it a little bit easier to edit. Okay, and then let's see, I think all of these go away, right? Because all of these are connected to the satellite controller. Well, via port expanders and whatnot. Okay, so let's see, the ref clock, we have an OE and we have the frequency select connection. Right, so let me go ahead and get rid of the stuff that we don't need here. So this will be ref clock FS. Okay, and what's the IO standard for those? So the ref clock connections are, let's see, here we go, QSFP 0 FS. So it's all LVCMOS 1.8. Interesting. I really liked LVCMOS 1.2 on the 1525. I think these are all 1.8. Okay. And I actually have been wondering, does it make any difference for the LVCMOS, at least, what the number is? Because it seems like that really only depends on what the IO bank voltage is actually connected to. So the FPGA is not going to have any control over that. It's going to be hooked up to whatever the board designer hooked it up to. So if you put 1.2 instead of 1.8, does that actually change anything in the bit file? Does anyone know? I don't know about that. I mean, obviously it's probably better if it matches, but I don't think there's really any problem if it doesn't match, as far as I'm aware. Although maybe it has to do with the calibration of some of the other stuff. So if you want to say IO standard LVCMOS 1.8, drive, whatever, slew, whatever, maybe those values have slightly different effects depending on the voltage selection here. Anyway, let's see. So this is the ref clock OE and FS. So OE is H32 and FS is G32. We do H32, H32, and G32. Okay. And let's do the same thing for this other guy here. Comment all of these out. And same thing, all of these control pins go away. Now this also goes away, right? Becomes ref clock FS. And Evan says it's for DRC only. Yeah, that's kind of what I figured. Okay, because I've definitely gotten warnings on some boards for mixing those IO standards. which I think it's the, what board was it that was causing a problem with that? I think it was the Digital Atlas board. The LEDs are mixed across a couple of different I/O voltages. So you always get a warning about that if you actually set that correctly. Let's see here. So I guess it will check to make sure you set them the same for pins that are in the same bank. And that's like an error, I think, if that's wrong. But then it will also give you a warning if you assign pins with different I/O standard voltages into the same port, basically. Okay, let's see, what pins were this? This is QSFP 1, OE bar H30 and G33. H30 and G33, okay. And I2C. I'm gonna get rid of that. And then PCI Express. Let's see, what is going to be the easiest way to do this? Actually, here's what I'm going to do. Comment all of these guys out. And you can see why I operate in Sublime Text most of the time instead of in Vivado. I don't think you can do this kind of selection whittling from Vivado. Let's see, so the PCIe ref clock, I was just looking at that here. I'm going to go ahead and add both of these. So we've got, for reference, I'm going to copy that temporarily. So we've got a couple of different connections here. We've got ref clock 0 and ref clock 1. Okay. I'll make these number 1. And let's see, ref clock 0 is AL14 and AL15. And the other one is AR14 and AR15. Okay, and we'll ignore the other synchronous or the asynchronous ones for now. Okay, and then the reset line, that is going to be, where was that one? Reset. BH26. BH26. Okay, so we got the reset and we got these guys. Actually, let me just make sure I have the annotation correct here. So this one is 227, one is 225. 0 is 227, 27, and 225. Okay. I think these, it's not necessary to specify the pins for these guys, so in the interests of brevity, I will leave those out for the time being. However, I think I need to specify the reference clocks for the transceivers. Let's see, where was that? Okay, I'm looking at it right here. So we've got the SI570 and the other ones. So I'll do this real quick, copy that. Okay, so QSFP 0, ref clock 0. This is going to be, well, they like specifying N first. I like specifying P first. So that's T42, T42, T43. And then the other one is R40 and R41. And same thing here. This is P42 and P43. Right, and then M42 and M43. Okay. That looks pretty good. So I can go ahead and think, oh, let me put the actual sites in here. So this is site 134. And this is site 135. Okay. So that, I think, is going to work. Let's see. And so what we're going to do is we're going to try to run these on the 161 megahertz input. So I'll go ahead and uncomment all of that stuff to get two 161 megahertz reference clock inputs. So we got those guys, and we have the PCI Express connections here. Okay. Right, so now let's take a look at FPGA.v and start deleting stuff. We have no GPIO, all that goes away. Okay, I think this is running on ref clock, it's gonna be ref clock 1, so let's go ahead and change this where it appears to ref clock 1. And there's a reset set connection, and that looks good there. Well, except all this needs to go away, right? Okay, QSFP0FS. That's only one pin here. Okay, and same thing here. Okay, there we go. And I need these two pins, and all of that goes away as well. All right, that's a start. Okay, these are going to be the same. I'm not going to touch that. Everything else should be the same. So one thing that I'm doing on here is the transceivers need to have a free running clock, I guess as part of the initialization procedure. So we need to get a free running clock from somewhere. And on this particular board, the way I decided to do that, at least on the 1525, is to pull the reference clock out of one of the reference clock inputs for the MGTs. Let's see, so this is the QSFP0 MGT ref clock input. How did I do that? So these are the two input pins, and then I have the main reference clock, which is fed to the actual transceiver instance. And then I took ODIV2, although it's not actually divided by 2. By default, I think it is not divided by 2. There's a parameter that specifies that, which I guess I haven't specified, but whatever, it works. That goes through a buffg, and then I send that up to an MMCM to convert it to 125 megahertz. I probably didn't need to do that. I probably could have used it at 161 megahertz without changing it. Actually, now that I'm looking at this, I'm going to use only one of the QSFP reference clocks for the time being, so I don't need to modify as much of this code. All right, so I'll comment these guys out. Okay. So let's see, we got the PCI Express reference clock set up. We got these reference clocks set up, and I commented out a bunch of stuff. So let me finish commenting stuff out, and then we'll see what we'll see about the next step here. So let's see, no GPIO connections, no I2C connections. That goes away. Let's see, the GPIO stuff is handled somewhere in here. Let me see if I can remember where that is. Okay, sync signal and debounce switch. Okay, so there's no switch connections. That goes away. There's no I2C connections, so that goes away. Let's see. Oh, right. Another annoyance on the 1525 is that you actually need to hold the clock generators in reset for a certain amount of time for those to work correctly and to actually select the frequency that you want. So I had to use the startup module here to get and use a configuration clock. So I had some free running clock to time that operation. In this case, I don't think we need to do that. I'm not going to remove that for the time being though, because it doesn't really make too much difference. So no I2C connections, no interrupt connections, no module present connections. Okay, so basically all that goes away. Okay, what else? That's MMCM reset. Okay, so that holds that for a while and drives, that drives also QSFP ref clock reset. Okay, is that connected to anything? Yeah, okay. So, well, first thing is FS needs to be changed to ref clock, FS, and then reset is going to be OE, not reset. I need to make sure I change that elsewhere. Let's see, how did that need to be tied? That one? Okay, let's go back and take a look at the clocking section real quick. Clocks. Okay, so OEB, active low, so that needs to be tied low. And then the FS pin, this one is saying tie it high. But I think, and this one is saying tie it low. Which documentation do we look at here? Which one is correct? Oh, this is highly annoying actually. Okay. So this one is saying quite clearly FS1 gives you 161. This one is saying FS0 gives you 161. I'm hoping I don't need to get out an oscilloscope to figure this one. Don't you just love that? Alright. I'm going to take a guess that it's 1. And if it doesn't work, then we'll invert it. At least there's only 2 possibilities. Actually, here's what I'm going to do. I'm going to set one of them in each way, and we'll see which of the 2 links comes up. Oh, actually, I'm only using one reference clock, so never mind, that won't work. Alright, I'm just going to guess that it's 1, and we'll see if that's correct. Let's see. What do I need to do next? Oh, right, I need to check to make sure I renamed that. I didn't rename it, did I? That should be OE. And then let's check the XDC file. Did I rename it here? I renamed one of them. Okay. Alright, there we go. So that looks good. And now let's take a look at what gets passed through to the core logic. I think I deleted most of that. Got all the PCI Express connections. And now we can delete all this stuff here. That goes away. And do the same thing here. All of that goes away. Okay. Cool. Well, I'm not the only one that makes typos. Or Xilinx is not the only one that makes typos. Okay. So that's that. And then an FPGA core. Since we deleted all that stuff, it also needs to be deleted here. No I2C, no GPIO. That goes away. QSFP 28 stuff. Let's see. I didn't make a typo here. Okay, that's good. So all that goes away. Alright, so let's see. There was the I2C stuff and the module control stuff that needs to go away. So here's I2C and the module control pins. That goes away. Let's see here. But basically all of this goes away. There's no GPIO. That goes away. And again, all the GPIO here, that goes away. And all the GPIO here also goes away. That everything. No, I think there's a couple more instances. Yeah, here we go. Alright, I'll comment it out for now and delete the rest of that later. Okay. Let's see. I think the next step is all of the IP then. Alright, so there's a couple of things that's necessary for this to work. This is a 10G design, so we have both the PCI Express interface and then the actual transceivers for the Ethernet connections. So let's see. I'm in the process of converting everything to using TCL files to create the IP instead of XCI files. I figured I might as well do that when I'm converting everything to run on Vivado 2020.1. So just kill 2 birds with 1 stone. Gotta regenerate everything anyway. Might as well do it in a more flexible way. So I think there's only one change that needs to be made here. There is a different PCI Express IP core on the HBM parts. It's PCIe 4C because it supports their CCIX thing and actually supports PCI Express Gen 4. Unlike the UltraScale Plus parts that were supposed to support PCI Express Gen 4, but actually don't. Yeah, okay. So we need to do that, and then we need to make the corresponding change here. Let's see. PCI Express IP core is here, so we make that same change here. Okay. Let's see. And those lines can be deleted as well. Okay. Okay, so this one I think is now correct. We got this set 8 GT per second, so that's Gen 3, X16 link, rattling off. Eventually, we might change that. I need to do a lot of work to support that. Client tag on, 512-bit interface, 250 megahertz. We got the subsystem ID and vendor ID set, and network controller. Yep, okay, that looks pretty good. Okay, so that is that. Now for the transceiver instances. Let's see. So first of all, on this card, oh, there are actually 8. That's right. We are going to be running on the 161 megahertz ref clock. And for now, we're going to generate 10.3125 for a 10 gig operation, which is fine. Question is, what are the sites? Let's see if it gives us what the actual sites are here. Doesn't look like it, does it? Okay, so here's what we're going to do. Time to fire up Vivado. I'm going to comment out that TCL script for the time being. Let's see, I think I had, there we go. This one is sitting in this directory already, so I'm going to go ahead and, let's see here, force opt Xilinx Vivado settings. I make the Vivado project so we can open this up in Vivado and figure out what those transceiver sites are supposed to be. And after that, we might be ready to try building the design. Nope. Oh, I forgot to change the part. Let's see. Is that in the XDC file, or do I need to do more digging to figure out what the actual part is? Let me see. I also have the XML files for the board here. The part may be specified in here. Ah, here we go. That's what I want. We'll take that and we'll put that in. I think I have a comment here, right? This is the AU280. Okay, and then this also goes in the make file. All right, let's try that. Make clean. Make FPGA.xpr. Okay, let's try that. So I know some people are big fans of using Vivado in the non-project mode. I've been using it in project mode because it's nice to be able to just pull up Vivado and hit build or whatever without having to rebuild the whole thing. That seems to get the job done just fine. Let's see. So this is now importing the IP. Let's see if it'll set up the PCI Express IP without complaining bitterly about something. Let's see, I did rename that reference clock, right? I think so. That goes through the clock buffer here. Yes, I did rename it. Okay. And I have the corresponding file, the corresponding thing uncommented here. Okay, that looks fine. All right. Okay, so now I can fire up Vivado. Like that's done. I'm sure we're all aware Vivado is not the fastest piece of software ever. Okay, let's see. Keeps popping everything up on the other monitor here. All right, so let's see. What we're gonna have to do is pull up the GT wizard and we'll see what that looks like. Okay, so there's a PCIe 4C UltraScale Plus module. Let's see if that came up with the correct settings. Presumably it did. Okay, I don't know if that's right. That even let me drop that down? But there's only 2 things in the list. Okay, well that's fine. 8 x16. That looks good. All of the straddling stuff is turned off. When I was doing some early development of the PCI Express stuff, I forgot to turn one of these off, and it totally didn't work, and it took me a few hours to figure out what the heck happened. Yeah, that's annoying. Anyway, so these look like they're set correctly. And yeah, that's set up correctly. Yeah, that looks good. Okay. So now what we need to do is generate the transceiver IP. So I need the GT wizard. Come on. What is Vivado complaining about here? There we go. So let's see, where, oh, I don't have that file open at the moment. I need the GT wizard ultrascale 0.tcl. Okay. So let's see what we have in terms of the physical resources. Wow, that's interesting. So they have basically all of the transceivers totally disabled, except for the only ones that are actually wired on the board. Interesting. Okay, so it looks like the sites are X0Y10 and X0Y11, and we can see bank 135 and bank 134. Having all these different names could make things really confusing, because the GT Wizard TCL files want these X0Y whatever numbers, but the XDC file only has the bank number in it. It's it can be kind of annoying to keep all that straight. Okay, so let's see. How are we wiring this up here? So we're going to use the ref clock 1 on site 134, and we need both of these. Okay, so 134 is here, so we're going to use ref clock 1. It's gonna let me select that. There we go. This one we're going to use ref clock 1 of the adjacent. Okay, there we go. Adjacent site. And QSFP 0 is on site, what is this? Site 134. Okay. Okay, so that looks pretty good. And then this is set to 125. Okay. Well, let's see. I guess I can go ahead and... this doesn't make too much difference, but I'll just walk through what you need to do to configure this appropriately. So what we can do is start with 10G base R, which is just a reasonable starting point. If we're doing 10G base R, we might as well start with 10G base R. I actually don't know if there's really any difference between the transceiver settings between base R and base KR. Because KR does FEC, but that's done at the PHY level and not at the transceiver level. Anyway, so this is set correctly, 10.3125. The reference clock we're using is 161. So assuming this cooperates, 161. And then this complains. Think about it, then it complains. Okay, put this on 161. It would be nice if it just also selected 161 instead of saying, uh-oh, you can't do that. Okay, so we have that. And then we need async gearbox for 6466, and we're going to set both of these to 64. There's one. One. Another one. Set these guys 64 as well. There's one. And there's one more. Okay. Excellent. That looks pretty good. Leave that alone. Physical resources. Didn't I just configure this a minute ago? I guess to start from scratch blew it away. Let's try this again. Okay, so this we're using MGT ref clock 1. Here we go. And then the ref clock of the adjacent site. Double check, make sure that's correct. we're using the ref clock on 134. 34, okay, perfect. We can see here, there's the ref clock input, feeds the PLL in both of these channels, which then feed the individual sites. Okay, perfect. Optional features, we're fine. Then all this is good. Okay, so now I'm going to hit OK here. Now, for those of you who are new to doing TCL IP, I'm going to show you how you get the TCL command for configuring the IP the way you want it. So we let this do its customization. And I'm going to cancel the generation as soon as that pops up. Cool. Skip. All right. So Vivado writes out these log files as it's running, and these list all of the TCL commands that it's run, basically. So if we go in here, we have setting up the IP, right? Create IP, and then we set all of the parameters. I'm going to copy this second one. I think the first one is exactly what's in the file already. And then we just need a couple of the values of these guys. So select all of these guys. Oops. Much. Okay. Okay. So let's see, I'm also going to go ahead and put all these backslashes in here. Okay, so we need a channel enable. Oops, that was the wrong slash, wasn't it? There we go. Okay, so we need a channel enable. Select all the appropriate channels. Actually, I'm also going to tab these in. Okay, so channel enable, right? That looks good. The RX and TX master channels apparently not specified. Okay, I think this was 40. This is X0. Okay. Line rate and ref clock and the other settings, that looks good. And then we just need the ref clock source. So these two, and we'll go ahead and replace these two lines. And then I think we're probably good to go. All right. So that's the TCL command to create the IP. Hopefully that'll work. So we go to the makefile now and add this back in. I'm going to close Vivado. See here. Okay, get out of Vivado, and as soon as this exits, we will try that again. Come on, how long does it take to exit Vivado? Okay, make clean. Then I run make again. All right, so this is going to attempt to build the entire project, so this may take a few minutes. In the meantime, I'm going to see if I can get my my development computer running while Vivado is mulling over things here. You might just need to reboot it. Back in a sec. All right, booted it. We'll give it a couple of minutes to come back, and then we'll see if we can talk to the card. Well, it takes a minute to boot. See what that does. Let's see. Well, I don't need that anymore. It's one thing that I like to do while Vivado is running is just look over the code, because it's quite common that I will have missed something and it'll jump out at me and I'll be like, oh no, let me fix that and restart Vivado before it gets too far along. Well, I guess the other thing I can do actually is update the test bench, and we'll see if that runs. Actually put this on my other monitor so I can monitor what Vivado is doing. Okay. So let's see. Test bench, this tests FPGA core. The main thing we need to do here is remove all of the extra control lines that are not used. So let's see, I use myHDL for all of the simulations because that means you can use Python as the test bench. It doesn't need to be synthesizable, so why restrict yourself to operating in Verilog versus operating in a higher level language? So if I go in here, clear out all of these signals we don't need, then we'll run the test bench and make sure that passes. So that's that, and then we also remove the module present and interrupt signals for both modules. Let's see. No LEDs. Let's see here. Some more module connections here. Okay. Let's see, and then we also have some additional connections here. Let's see. I need to remove the connections here. This is the connection to the actual co-simulation part of the test bench. That goes away. QSFP 0, same thing there. Okay. Now let's see here, same thing. Get rid of the I2C interfaces, and I get rid of, see, I still need those guys. What are those? Okay. And let's see, I2C and LED, don't need that. All right, I2C, LED, and the QSFP control connections, there and there. QSFP control connections here. All right, I think that may be all I need to do. So I'm going to go ahead and try running this, and we'll see if this simulation is happy. I missed something. What happened? Let's see. Oh. I didn't really modify this thing. So let's see. That, and I get rid of the control connections down here as well. That goes away. And that goes away. Oops. There we go. All right. Nope, still no good. FPGA core. Okay, so this is actually, line is that on? 1864 and 1865. Okay. Okay, let's try that again. All right, here we go. Now it's running. So this runs through all of the PCI Express initialization, and then, well, it enumerates the bus and initializes all of the PCI Express control registers and whatnot, everything in configuration space, and then it goes through and initializes all of the internal NIC configuration, and then sends and receives a bunch of packets. So what we're seeing here is all of the PCI Express traffic to the card. These are the ultra-scale PCI Express frame formats for a bunch of register writes, 32-bit register writes. And now it's actually trying to send and receive packets. Or no, not yet. It's setting up. It's still setting some stuff up. So we'll let that run for a while. It looks like the host is up. So let's see if we can talk to the U280 card. Okay, let's see here. lspci. Oh boy. There we go. That's the card. Let's filter by that. Let's see what it looks like. Oops. Okay. There we go. So this is what the card looks like over PCI Express. I'm not sure how much you guys know about PCI Express, but basically what seems like YouTube is not happy for some. Hang on a second. Stop the file synchronization and see if that helps with the stream. Okay. That's still running. Vivado is still running. Okay. All right. So what this is showing is basically a dump of. Oh, here we go. This is actually now sending and receiving packets in a test bench now. So it looks like the design is probably working. We want to look at the waveform view of that later, then we could do that. But okay. I mean, the only thing we did is removed some top-level connections. So unless I really screwed something up, that working is not particularly surprising. What we're really testing is to make sure that Vivado set up all of the interface components correctly and all the I/O pins are set correctly so that the core data path works. Okay, anyway, this lspci program, it can list out all the devices on the PCI Express bus, and it can also talk to the configuration space where it will show various configuration parameters on those devices. So this shows the bar, the base address registers, the memory regions that are assigned to that particular device. So you can see the physical address and the size of each one of those. And then all of the PCI Express capabilities in the configuration space. So it's got power management. MSI is for interrupts. You got MSI and you got MSIX. So this one's just MSI, currently disabled, but it can be enabled. There's only one. That's interesting. So the Alveo framework only uses a single MSI. It's a little surprising, actually. I would think they would provide a few, but I guess not. Then we have the PCI Express capabilities, and let's see, the PCI Express capability, and there should be an extended capability as well for PCI Express. Maybe not. Well, there's secondary PCI Express. Yeah, okay, anyway. So this one has a number of important parameters to take a look at. One of them is the max payload size and max read request settings. So dev cap, this is a read-only register that specifies the capabilities of a device. So the device, this is how the device tells the operating system, all right, I can handle payloads over PCI Express of up to 1024 bytes. And then what the operating system will do is it will then write into dev control what payload size the card is allowed to use. So it shouldn't write a value bigger than 1024. In this case, it's set to 512. Which is actually kind of interesting. On most of the other systems that I've used, the max payload size is either 128 or 256. Now, one word about this particular parameter, the max payload size and the max read request size, they're both 3-bit fields. So they can be set to one of 128, 256, 512, 1024, 2048, or 4096 bytes. Those are the only allowed settings. So 128 bytes is basically the minimum. So every machine, it has to support that. And for older machines, they're all set to 128 usually. For some of the higher end machines, I think basically all the machines that we have in the CSE machine room, which are running actually halfway decent CPUs, they are all set to 256 bytes max payload size, which is kind of interesting. Let me see here. I can do an lspci on one of the CSE machines right now real quick here. And we can check to see what that says really quick. Okay. So this is running on a machine with an Intel CPU. This is running the Corundum design. You can see by the, this is the number that I've been using in Corundum. It would be nice to get a proper PCI Express vendor ID, but whatever. This works for the time being. This one is only set to 256 bytes. So the only ones that I've seen, the only machines that I've seen that will actually set it to 512 bytes are these AMD EPYC based machines. So if we do ls CPU here, this one is a Xeon Gold 6138, which is a pretty high-end CPU. So it's kind of interesting that it only sets the max payload size to 256. But on the flip side, this only supports PCI Express Gen 3, whereas this one theoretically supports PCI Express Gen 4, so go figure. Not sure what the story is with that. Anyway, let's see. So Vivado is actually synthesizing the code now. It hasn't run into a problem yet, so we'll see what that looks like. Okay, while that's running, let me get out of this guy. What I'm going to do is fire up the hardware server and see if we can talk to the card through Vivado. Alright, so the cool thing about the hardware server is it means that you can access hardware running on a different computer over the network. Let me see if this is running out. This is running the correct version. That's good. Okay. Alright. I also need to figure out what the IP address of this machine is real quick. Actually, maybe I'll do that first. Okay, so it's probably going to be this guy. Okay, so I'll get the hardware server running, and I'll go ahead and open up, source Vivado here. Okay, so now this is opening up Vivado. Again, we'll have to give it a second, and then we'll see if we can talk to the card over the network. This is a super useful technique when you're doing stuff remotely, even though it's possible to load code onto the FPGA through various interfaces and frameworks and whatnot. Having remote JTAG access is very important if you want to use, say, the integrated logic analyzer and other debugging tools. And even though the logic analyzer, the ILA is a little bit limited, it is just an incredibly powerful capability to be able to run that on the FPGA and get even a small capture of the internal state. Okay, so that's here, and this is running, right? It's running synthesizing. Okay, so what I'm going to do at this point is I'm going to open the hardware manager, and we'll see if we can talk to this card. Open target. So I can't use auto connect, unfortunately. That only works if the card is plugged in locally. So let's see. The IP address that I'm going to use is, what was this? Oh, I had it right here, didn't I? Okay. I think it's this one. If it's not this one, then I'll try the other one. Okay, there we go. That did detected something. Okay, there we go. AU280. Yep, that is the card, all right. So if we do that, and we give it a moment. And there we go. So we're connected to the card, and now we're just waiting for Vivado to finish up synthesizing and running the place and route so we can load the design on the card and see if it actually works. Let's see, what else can we do in here? Let's see, so this is actually, so another thing you can do over JTAG is you can talk to the system monitor and you can look at various supply voltages and whatnot on the card. So this actually reads out the FPGA temperature. So it's about, let's see, right now it's about 38 degrees C, which is quite reasonable. Core voltage is around 0.85 volts. Let's see, I think that's core voltage. Let's see here. Yeah, VCC int is about 0.85 volts. VCC aux 1.8, VCC BRAM 0.85. And I guess it doesn't measure anything else. Interesting. Okay, well, that looks good. We can talk to the card. Let's see. Now we just need to wait on Vivado, which that could take a few minutes probably. Let's see. What else could we do in the meantime? I guess we can take a quick look at the simulation result here. When the simulation runs, it also generates a waveform dump. Let's see here. Test FPGA core.lxt. There we go. Okay, so this is the waveform dump of running that simulation. So this will have all of the packets that were sent and received and all of the PCI Express traffic and everything else. So if you're actually interested in debugging a design and you want complete visibility into what's going on, you know, this is how you get that. With the ILA, you might be able to look at a particular interface, but with a simulation waveform dump, you can look at everything. So let's see here. Let's see. Where is that Vivado? All right, I'm going to put it over here so I can keep an eye on that. All right. So I guess while we're waiting for Vivado, I can walk through some of the components of the Corundum NIC. So when a packet is being sent, well, okay, so there's a couple of main paths that the driver uses to talk to the design running on the FPGA. Well, the path from the host to the FPGA is through AXI lite. So if we look at the hierarchy here, let's see, where is the AXI lite module here? Okay, PCI Express US AXI lite master. Okay, so this module is responsible for receiving the PCI Express traffic that is destined to the base address register on the card and converting that to AXI lite operations. So any register reads and writes from the driver, you know, need to pass through this module. So let's see here. This has S-axis CQT data. So this is the completer request traffic from the host. So this will be read requests and write requests from the host. They come in here, and then this module will convert it to an AXI lite read or write. So as the packets come in, then there is the AXI lite interface here, and it's either generating reads or it's generating writes. So the first thing that happens when the driver is loaded is it reads a bunch of configuration information out of the FPGA design. This is, in some sense, a relatively, I don't want to say unique necessarily, but it's a very useful feature of the interface between the Corundum driver and the FPGA. So for a lot of like ASIC-based NICs, most of the configuration settings, and just in terms of, you know, how many ports are there, are fixed when the ASIC is manufactured. So it doesn't really make sense to read a bunch of configuration information out of the ASIC. But with Corundum, since it's built on an FPGA, there's a relatively high probability that somebody's going to want to change like the number of ports or the number of queues or something like that. So on an ASIC where that's fixed, you don't necessarily need to read it. Maybe you have a little table in the driver, and it's like if you see this PCI Express device ID, then you know you have this ASIC which has this number of queues and whatever. But with Corundum, you don't always have to set the parameters the same way. So one option, let me actually show you the Corundum code that does some of this. Oh, okay, synthesis completed. Well, now it's going on to the next step. Okay, so let's see. Okay, so Corundum exposes a number of different pieces of information. Now, the firmware ID and board ID and whatnot, they could be used to look up, you know, a table. And if you get a match in the table, then you know what the configuration is. And to some sense, we have to do this because the interfaces available on different boards are going to be different. Some boards have, you know, direct connections to the QSFP modules in terms of I2C interfaces. Some of them go through I2C muxes and things like that. So for that, it's okay to have a table. But if you want to change the number of interfaces, exposing this via a read-only register makes a lot of sense, because the driver, when you load it, can just read the register and say, oh, this design has one interface or two interfaces or 8 interfaces, and then it can automatically allocate, you know, that number of interfaces and assign all the addresses appropriately and whatnot. So there's a couple things that are exposed here. One of them is a number of interfaces. I guess there's not that much exposed in this particular one. Well, actually, there is this IF stride, which is it's basically, it's not a pointer to the next interface, but it's the step, if you will. So if there's 4 interfaces, and they're going to be spread equally through the PCI Express bar, then IF stride would be, you know, 1/4 of the bar size. So being able to read this from the driver means that basically the FPGA code will automatically figure out all of its address assignments and then expose that to the driver, and then the driver will automatically figure it out. So that means that you can have one driver that supports many different boards and even many different configurations on the same board. Okay, so that's what we have going on here. And that's the first thing that happens when the driver is loaded, is it reads all of these configuration registers, and then based on what it reads, it then has to perform a bunch of initialization operations. So all of this is going to be initializing all of the Q state. So that's writing, so the driver will allocate memory for storing all the transmit and receive rings, and then it has to write the address and that associated information into the registers on the NIC. So that's what's taking place. That's what's taking place in here. And then this part is actually sending and receiving packets. Okay. So we could follow sending and receiving an actual packet, but that's maybe not today. That touches a lot of stuff. But while Vivado is working on the 10G design, we can actually take a look at the 100G design and make the same modifications to that. Hopefully this won't take too much longer, but we'll see. Okay, so the 10G design versus the 100G design, most of the stuff I think can be just copied over. The main thing for that is going to be the actual Ethernet interfaces here. Oops. So on the 100G design, we use the CMAC cores because I didn't feel like making a 100 gig Mac. That's a little bit more complicated than I want to deal with. Okay, so let's see. I'm going to copy this for reference, and we'll see if we can set this up the same way. So I think I can basically directly copy this. Everything I need is here, except I need to put that one line back, or a couple lines back in for the reference clock. Okay, so everything is the same, except we have an additional reference clock, and then I need to change these TCL scripts. Okay, so QSFP 0 is on site 134. Well, that doesn't help me at all, does it? Okay, but that's the lower numbers. Okay, that's perfect. So I can go ahead and change this to, this is going to be 40 through 43. Oh, and this is X0. 40 through 43. Oh, I don't know what the CMAC number is. All right, well, Vivado is running. We'll take a quick peek at that. I can go to IP catalog here. CMAC. And we gotta wait for this. Okay. So the CMAC core, this is responsible for converting, you know, an internal interface, which the CMAC supports 2 different interfaces, either this segmented LBus interface or an AXI stream interface. I guess older versions didn't actually support AXI stream, but there were enough people like that complained about the CMAC being the only device in the entire library that used LBus. And converting that to AXI stream is kind of a pain. So Xilinx actually decided, all right, maybe we should give an AXI wrapper for that. So So let's see. I'm going to change this. Come on. Why is this being so slow? I'm going to select CAUI4 because we're using 4 channels. Okay. There we go. GTY, duplex, and AXI stream. Okay. And the main thing that I need to do here is check the GT core selection. So there's actually several CMAC instances on here. Although, let's see. So we've got 5 CMAC instances, but only 2 sets of transceivers. Interesting. Okay, so the default one is recommending site X0Y7 and sites Y40 through Y43. Okay, so I got Y40 through Y43. I'll put that over here, 40, 41, 42, 43, and I will put that there. Okay. All right, so I think that will work. And then the other one is going to be, I think there's only one other option, right? 44 through 47. And I will have to pick a different CMAC for that, so probably X0Y6. All right, cool. So X0Y6. And this is 44 through 47. Oh, is that already correct? I guess so. All right. Well, we'll have to see if it generates the core correctly in that instance. Okay, so I'll save that. I will save that. And let's take a look really quick at the HDL code here. There's a bunch of stuff I need to delete on this one as well. Again, no GPIO. Ref clock 1 on both of these. Let's see, all of these control pins go away. Ref clock reset, this is not a reset, this is an OE. And this is, oops, let's see. Ref clock FS, okay. All right, so that's that. And then I need to remove, again, all of the GPIO stuff. That goes away. And let's see. Oh, I also need to change the PCI Express IP core name, right? This is PCIe 4C, and that also needs to be changed here, PCIe 4C. Okay. Let's see. Okay, so this is now OE. And this is going to be set to 0 because it's OE bar. Okay, and then the FS settings here. Will be, okay. I don't know if I need to tie that high or low. That's rather annoying. It's one thing if there's, like, you know, a small difference, but if you're gonna confuse whether you tie something high or tie something low, that's a little bit more annoying. Okay, let's see. So again, we lose the GPIO and I2C connections and the transceiver connections here. So in this case, we've actually moved. So one big difference between the 10G design and the 100G design is in the 100G design, the MAC is at the top level in FPGA.v, versus in the 10G design, I'm using my open source Mac, so that sits in FPGA core. So for the 10G design, we bring the AXI, or sorry, not the AXI interface, the what is it called? The XGMI connection across from one module to the other. Let's see, where are these? Yeah, RxD and RxC. So we have a 64-bit data plus an 8-bit control, and it's a single direction. So TX goes one way, RX goes the other way, and then we have to bring the clocks across as well. For the 100D design, since we're using the hard Mac, that has to sit in the top level module. So the nice thing about the 10D design is that it can be completely parameterized. You change the number of ports, it'll bring in more Macs as necessary. For the 100D design, you have to instantiate them individually. But, I mean, the card only has 1 or 2 interfaces, so it's, you know, not that big of a deal. Okay, so that's fpga.v. Now we go to fpga.core, and we do the same thing. That goes away, and we lose all of the control signals as well. Also, I will mention that Corundum currently does not support PTP in the 100G variants, and that's something I'm working on. I have a couple of things I need to rewrite to make that work. So yeah, at some point that will be supported. The main sticking point is the clock domain crossing for the PTP timestamps. I've probably rewritten that module about 3 times already. I need to rewrite it one more time, and hopefully it'll work at the required clock speed. Part of the problem is that for the 10D design, everything runs at 156 megahertz, but for the 100D design, it runs at 322 megahertz, which is a lot faster. And that big of a jump is a little bit too much. Okay, was there a LED connection in here somewhere? Oh, maybe it was down at the bottom. Okay, so this has the PTP clock, but it doesn't have any of the other PTP infrastructure. Okay, so that looks reasonable. I guess I can also see if Vivado will be happy with that. How's the other one going? It's doing area optimization. Hasn't started routing yet. I think it's more than halfway through. It's a small design. Let's see. Okay, so we'll check the IP settings, then kick off the 100D design, and we'll see what that looks like. I guess we have Vivado up and running here. Let's actually take a look at what the resource utilization looks like on this part so far. Okay. I'm used to Vivado supporting the utilization information, at least from the synthesis run. Well, let's see if we can locate that in the log files. Oh, something was not happy. Oh, again, I forgot to change the part. All right, let's see here. So I need to take that and paste that the make file here. And then that might work. Oops, I just want to make just the project file. Okay. Let's see here. So I'm going to take a look at the output of the synthesis run here and see if there is a report for the utilization. All right, so we have cell usage. But that doesn't give percentages, does it? Oh, FPGA utilization synthesized. There we go. Yeah, so 4% of the LUTs. Yeah, that shouldn't take very long to finish place and route. Seems like it's mainly placement that takes a long time, and routing after that is not too bad. All right, so that'll take a few more minutes to finish. And this one is still not happy. Oh, I think I missed a line. Okay. That's the wrong TCL file. I want this one. Yep, there we go. PCIe 4C. I don't know why it is, but sometimes these more trivial changes seem like they're more difficult to implement. The problem is you don't put enough thought into it, so you miss something here or something there. I don't know how many times I've caught some really stupid mistake once Vivado is, you know, halfway done working, and then I'm like, ah, crap, that's not going to work. Let me fix that typo and restart Vivado, and it runs for like 10 or 20 minutes, and then I find another typo. Or I realize that my little change added another typo. Okay, let's see here. Oh, I ran a full make. I didn't want to do that. We gotta check to make sure the CMAC settings are fine. And then we can kick off full tools again. And the 10G design is, oops, still working. Okay, let's see here. Open this up, see what it looks like. Oh, I guess another thing that I need to do is set up a PCI or a device ID for the AU250 or the AU50 and AU280 boards. Well, I can do that later. It's not that big of a deal. Okay, let's see what we got now. Assuming this finishes loading everything. Okay. But I must have skipped a step somewhere. Oh, I forgot how to make clean. That's what happened. I'll try this again here. Okay, so it looks like the PCI Express IP is doing what it's supposed to do this time. Created the IP, but didn't set any of the parameters. Okay, now it's creating the Mac modules. All right, cool. Oh, not like something. Attempt to modify. Oh, I have the wrong. Thought I had the right sites. I have the wrong sites. These are X0, not X1. All right. Like I said, sometimes these really simple things, not putting enough thought into it, and you miss some silly stuff. Okay, I think that's right now. And the 10G synthesis run is still going. It's running, it says global routing now. So, alright, it shouldn't be that much longer for it to finish routing. Then we'll see if it works on the board. Let's see, that's for, where was, okay, there we go. Oh, well, leave that running for now. We make sure that the driver has been built. Okay, let's see, modules. Okay, there we go. Driver is built, so the driver is now ready to go. As soon as we get the design on the FPGA, then we can test it. Okay, this is now doing rip up and reroute for the 10G design, so hopefully that won't take too much longer. All right, we do Vivado FPGA.xpr. Let's double check all the settings for the Cmax, and we'll go from there. Any bets on how many iterations it's going to take? I think it's going to close timing at iteration 0. It's a very small design and a very large part. But sometimes it needs to go to iteration 1. And unless you're talking about the net FPGA, in which case I have to turn on the additional passes option, basically. So it goes through the whole first thing and then does an incremental placement change and then tries again. And even then it usually doesn't close timing. On the Kintex, let's see, the Xilinx X10, sometimes it also has a bit trouble. I gotta keep the number of queues relatively low on that one. Otherwise it doesn't always close timing. Okay, what do we got here? CAUI4, we got the correct reference clock, 125 megahertz DRP clock. Okay, all this is correct. All that's turned off. ANLT is off. I would turn that on, but I don't. They need a separate license for that, which is annoying. The nice thing is it does include RSFEC because that's part of the hardcore, and the Mellanox NICs don't work if you don't have that turned on. So it took a few tries to figure out how to turn that on properly, but it's on now, so we're good. Okay, and then this one is set to X0Y7 and X040 through X043. That looks good. Okay, and transcode bypass is turned off. That looks good. Okay, we'll check the other one and make sure it's on the other site. Let's see here. So this is 44 through 47 and using X0Y6. Okay, that looks reasonable. Pipeline registers on. Yep, okay, looks pretty good. And this all looks good. We got RSFEC turned on. All these settings are correct. All right. Cool. So we can go ahead and run make on that. We're probably not going to test that one on the stream today. I don't think. That's going to take a while to finish. Go ahead and put that one aside. All right, looks like it's almost done with global iteration 0. 6 overlaps. Come on, Vivado, you can do it. 1 overlap, okay. All right, so 0 overlaps. Did it close timing? This one usually closes just fine on the VC1525, which is a VU9P. The interesting thing to note is that, oh, that failed minus 0.2, but TNS only minus 3. All right, well, we'll see if we can clean that up. What I was going to say is that I usually have trouble with the 25G design, which is kind of interesting. The 100G design, which runs at 322 megahertz and has this huge 512-bit bus, seems to work fine. The 10G design at 156 works fine, and that is a 64-bit interface. Whereas the 25G design, which I have to run that at a 128-bit interface, in the PCI Express clock domain at 250 megahertz, and then that drops to 64 at 390 megahertz on the Mac side. That one causes more trouble, probably because 390 megahertz is rather high. I'm not sure if it makes sense to run that at 128 bits and make a new Mac. I don't think that makes sense. Probably it has something to do with the SRL crossing on that part. Okay, that got a lot better. PNS minus 0.8. Worst is minus 0.2. Apparently the U280 is a little bit more tricky. Not sure why that is. I'll have to take a look at the design when it's done. Oh, speaking of which, do we have... Nope. Placement is done. So we should be able to take a look at the post-placement utilization figures. Utilization placed. Oh, that actually went up quite a bit. Oh, well, that makes sense because one annoying thing about the synthesis numbers is that excludes all of the resources used by all the IP. So I get tripped up by that a lot. I'll go like, why is the placement utilization so much higher than the synthesis utilization? Well, the PCI Express IP core uses quite a few LUTs, and the CMAX also use some LUTs. So yeah, there we go. Okay, so we're using 11% of the CLBs. Still, a lot of space for packet processing or whatever. Again, Corundum is just supposed to be the host interface, so any packet processing you want to do, in addition to just getting packets to and from the host, you need plenty of space left over for that. Okay, let's see, what was that one? Okay, it's on iteration 3 now. Oh, okay, so this one at iteration 2, that was failing by a very small number. So hopefully it can fix that. Oh, Well, it's probably close enough to test that on the card and see if it'll at least, if the driver will load and talk to the card. And the Ethernet interface might not work because that clock setting still might be wrong. We're going to figure out which one of those documentation, which one is correct, if we're supposed to tie it high or tie it low. Actually, sometimes it can clean up some of these long paths. I need to take a look at what that is and figure out what it is, because that's annoying. One thing I have noticed is that sometimes it has a lot of trouble within the PCI Express hard IP core. So if you get a fail like that, at least for the Gen 3 by 16, it has to run the core internally at 500 megahertz, and it can sometimes have trouble closing timing for that, which is really annoying. It's one thing if it's in my code and I can actually do something about it, but if it fails inside of the hard IP core, then I'm like, well, I mean, what am I supposed to do about that? Oh, it may have actually closed timing. Estimated timing summary. Oh, okay. Interesting. So I think it does some critical path optimization. So if that closes timing, then we're good. And we'll see when I load that if it brings up the link or not. Let me take a look really quick. I think I have my AOC plugged in. Yeah, I got it plugged in on this side. It should be plugged in on the other side as well. Let's see here. So what card would that be? I think that's coming in as ENP1. Yeah, so ENP65 is my 10G NIC, and one of those links is up. One of them is down. That's as expected. Because I have something else plugged in there. And then for the 100G NIC, this guy is a Mellanox NIC. We'll take a look at that real quick in lspci. Interestingly, it shows up as bus number 1, even though it's not the first PCI Express slot. Slightly confusing. But yeah, so this is a ConnectX-4 NIC, Mellanox ConnectX-4. Dual port NIC, although there's no way you can use both ports at 100 gig at the same time. Okay, let's also see what ETHTool says about the device. This is how we check to see if it came up at the correct speed. So speed unknown, duplex unknown. We'll check on that again once the FPGA design has been loaded. Actually, I'm going to have to reboot that computer as well to get the bus reinitialized and to rescan stuff. One thing that I've noticed is that if you're reloading the same FPGA or the same PCI Express interface configuration, if you're not changing the size of the bars or changing any of the IDs, you're basically just uploading another variant of the same design. You don't necessarily have to reboot the computer. You need to unload the driver, and then you can do, at least in Linux, this seems to work pretty reliably, you can do a PCI Express hot reset, and it will cause the card to bring the link back up and rescan and whatnot, and you don't actually have to reboot the computer. Okay, this is now generating the bit file, so we're doing quite well here. Okay, so let's see. This thing still has not loaded anything. Why are you not showing me any reports? I don't know. I guess Vivado was just being Vivado. Alright. Let's see. So we'll just wait for this to finish generating the bit file. I think it also has to run DRC. For some reason it runs DRC like 5 different times throughout the entire process. Oh, right. So one consideration if you're going to use the PCI Express hot reset technique is this is at least a problem with servers. I don't think this is so much a problem with desktops. They can have management and monitoring subsystems that monitor the status of a lot of the hardware components. And what I've noticed is that for some of these machines, if a PCI Express device falls off the bus, then this has nothing to do with the hot reset script. If you just even reset the FPGA over JTAG to load a new design, it can trigger this. But when the device falls off the bus, on older machines, the subsystem, the lights out management or monitoring subsystem will detect that and usually like flag an error and give you an angry red light or something like that, which, you know, not really that big of a problem. But on other servers, it'll do that, and then it'll reboot the computer. Like hard power reset, you know, not a smooth, let's ask the operating system nicely to shut down. No, it just reset, bam, and there's nothing you can do about it. Well, there is something you can do about that, which I'll get to in a second. But generally, the IPMI stuff, it won't give you an option to go in and say, hey, if you could kindly not reboot the computer under that circumstance, that would be great. Usually they don't give an option for that. But what you can do is go look at the PCI Express slot that the card is plugged into. Let's see, if I do lspci-t, for example, you can see what I'm talking about. Let's see, so like here is the Mellanox NIC in at bus number 1. And it has two functions there. That's sitting in this root port, right? Which is bus number 0, device number 1, function 1. So if I do lspci-s00:01.1, this is a root port, right? PCIe port, and what you can do is flip some bits in here. It's like SERR and maybe a couple other ones. I can't remember off the top of my head. But if you flip those bits, then the port will not report the fact that the device that it's connected to has fallen off the bus. And then the IPMI card won't reboot the computer. So yeah, if you're working with Alveo cards or Well, yeah, okay. So somebody posted Echo 1 to sysbus rescan. Sometimes that's sufficient, sometimes that's not. So I have this hot reset script, which it basically does that. Actually, let me pull it up. The script is in this repository somewhere. Let me go hunt it down. Let's see. Looking under lib, FPGA lib, PCIe scripts. Okay, so here's a hot reset script. So it does a rescan, okay, but it doesn't rescan the entire system. It just rescans that one port. But what it does before that is it writes to this bridge control register at the upstream port, which triggers an in-band hot reset, and that actually resets the card. So unloading the driver and rescanning the bus, it doesn't actually reset the card unless the driver, resets the device as part of, loading or unloading or something. But if you issue a hot reset like this, it actually causes the PCI Express, the PCIe user reset line on the FPGA to toggle, and it will actually reset the design. I mean, not like as if you reprogram the FPGA, so anything sitting around in a block RAM is still going to be there, but it does assert that reset signal for most of the design. So that can get you out of a bind sometimes if your design hangs, and you can say, okay, how bad of a hang is this? Did I just get a state machine stuck in a weird state, or is there something else going on? You can fire a hot reset and see if that happens. I will say that's definitely saved my rear a few times. But yeah, if you load a new design on the FPGA, then you have to trigger the PCIe link to retrain and whatnot. And sometimes that might happen automatically. Other times you need to kick something. Okay, so somebody said sys device power control. Out of curiosity, let's see what's there. Well, okay, so I don't, that's probably not the actual path for that. Some motherboards will allow you to turn off the power to PCI Express slots, but this seems to be a relatively rare capability. So on the ones that let you do that, that would probably work. But I've not seen that ability on any machine that that I have sat in front of or connected to. So yeah, if you have that ability, then it works, but every PCI Express system can do a hot reset, right? So yeah. Oh, one thing that you can do, actually, since we're on the topic of PCI Express here, let's see here. Let's see. Where is PCI? Is that the one? Okay, so one thing that you will notice is that if you go and look at a PCI Express device, there is this thing called reset. But what is that? Why do you need to do this whole thing through, bridge control and whatnot to reset the device when you have this little reset thing you can send a message to? Well, this reset is what's called the function level reset. So this guy actually doesn't reset the card. What this does is it requests that the function reset itself, not the entire device, but just one part of it. It doesn't have to be implemented. Some devices implement it, but not all of them. And if they don't, then it doesn't work. And if you write a 1 to this reset file, it doesn't actually reset the Xilinx hard IP core. I've tried it. It doesn't work. If you set it up to support function level resets, then there's a dance you can do to get the reset command out and respond to it and whatnot. But yeah, that it takes a lot of additional work to actually support that, and it doesn't reset the entire device. Now it's possible that maybe if you do this reset on the on the upstream port that it would reset the device. I'm not sure if it would do that. I can experiment with that a little bit later, and we'll see about that. But yeah, I found that the technique of using set PCI with that script, it's worked basically every single time, and I've not run into any issues where it doesn't work. So, I don't know. Okay, so why does this say implementation is not started? This is a 10G design. I guess it hasn't refreshed something. Fair enough, but it did generate an output bit file. So let's see if we can load that on the device. We're still connected to the device, I think. All right, let me put this away. What's going on here? Okay, so I'm in, okay. This is programmed. It's programmed with the Alveo thing. So I'm gonna hit program device here. And let's see, where did that bit file go? There we go. So hit program. All right, so now that's doing its thing. And let me find the window I had open connected to the dev machine. I think it was, nope, wasn't that one. Here we go. All right, so once this is done, now I need to disconnect from the hardware server. Yep, why don't you do that? Cool. And I can close that. And this was at, that was there. Okay, cool. So I'm gonna go ahead and we'll reboot this guy. I have to give that a couple of minutes. All right, so that's going to reboot the machine. Didn't close the connection as expected. All right. Probably because it killed 0 tier first. Yeah, hot plugging. I don't know much about hot plugging. And if that needs to be done in BIOS, I don't think most, yeah, like I said, I don't think most computers will expose that. The most that I've seen, at least on these particular motherboards, these are halfway decent super micro server motherboards, is that they support various bifurcation settings. Interestingly, apparently they can also automatically figure out what the bifurcation setting needs to be. So, not sure how that works exactly. Now, if you change the bifurcation, that probably requires a reboot, because you'd have to, reassign bus numbers and whatnot. So actually, I did a little bit of poking around to figure out what is supported on, or at least how PCI Express hot plugging works, because the way all of the capabilities and whatnot are configured and the way addresses are assigned, it basically requires all of the devices to be present at the same time. You can't really insert another device somewhere. So if you want to do hot plugging, you basically have to somehow reserve some bus numbers and some device numbers at a particular spot in the hierarchy where you can, utilize those later. And you also need to register address base as well. Well, when you deconfigure the FPGA, it doesn't always do that. Say I just ran lspci after configuring the FPGA, and it still shows it in the tree, so there's still stuff there. I guess it's a little bit dangerous to reconfigure the FPGA without actually properly removing the driver first, but at least with Corundum, the way the interface between the device driver and the FPGA is set up, if the FPGA just kind of disappears randomly, it's not actually a problem because the driver will automatically configure stuff on the other end. So, okay, let's see if this came up. Oh, hey, all right, so this actually enumerated as the Corundum device, so that's a good start. Now let's see, I'm gonna do that, and then And there we go. Okay. Now I'm going to go into projects, Corundum modules. Okay. Let's see if this will load. Okay, it looks like that loaded. Excellent. So device is enabled. It read, well, the ID for the 1525 board, because I haven't updated that yet. These two interfaces, okay, loads all the Q counts. And okay, that looks pretty good. And since there's no EEPROM configured on here, it used a random MAC address. And that's actually something I got to figure out on these boards as well, is how to read the MAC address. It has a very nice sticker on there with a MAC address on there, but I don't know if it's accessible through an EEPROM or something else. Presumably, it's in an EEPROM that the system controller can access, so I'll have to figure out how to get that operational at some point. Okay, so that's that. Let's see if we see the interfaces here. IP link. Okay, we see ETH0 and ETH1. Okay. So one thing that I have not yet implemented in Corundum is even the ability to take links up and down and whatnot. So the link is basically always active and it ignores whatever this says. All right, so let me take a look at, where did I have, okay. Let's see if anything happened here. ETH tool, okay, it looks like the link didn't come up. Let me see here. IP link. Well, actually, I might need to set both of these up. And it looks like it didn't come up. Interesting. Well, that probably means I tied the FS pin the wrong way. And, well, not much we can do about that, I suppose. Either that or there's no optical power. Let me think. What I can do to rule out the optical power issue. If it didn't take the transceiver out of LP mode, then we're not going to get any light down the cable. So what I'm going to do is plug in my direct attach cable to the other machine, and we'll see if the link comes up. Okay, there we go. I have the other machine up and running, and I plugged the direct attach cable into that. Let me see if that's going to work. It might not. I might need to flip that pin and try it again. Well, I'll have to give that a minute. Well, at least there's only two possible states for that, so we'll try the other one. If it works, it works. If it doesn't work, it doesn't work. But at least it is coming up over PCI Express. Actually, I can do a couple of other things really quick here. There is the user space utilities here. Let me make sure these are up to date. Okay, so I can run mqnic-dump and see if that works. Kind of helps if I use sudo. There we go. That dumped a whole bunch of stuff. So this is somewhat useful for debugging. because it shows all of the internal registered states on Corundum. And I've had issues with schedulers hanging and some other stuff, so being able to do this is very useful. So yeah, it looks like we definitely have access to all of the queues on there. All right, fair enough. So it looks like the driver can talk to it anyway. The next question is whether the Ethernet link will come up. My guess is I may have gotten that pin state wrong, which means we're not going to be able to get this working today. But we'll see. Okay. Let's see. We got... what slot is that NIC in? I can never remember because these bus numbers don't make any sense. Let's see. lspci. Yep. See, the Mellanox is at C1. Which is what, the 132? Maybe. It's either 132 or 193. Well, I'll set them all up. NP 93, 0F0 up. And F1 up. And 132, F0 up, and F1 up. Okay. IP link. Okay, so 193, that one came up. 132, no carrier. 193, no carrier. And the other 132, no carrier. Let me double check that there's nothing else plugged into that. Yeah, I think this is the device. All right. Well, so that's a good sign. I guess maybe I did get it right. Let me see. Let's see. What should I do here? I will add an IP to both of these here. Yet again, sudo make me a sandwich. Let's see here. Okay. Let's see what happens if can I ping the other one? I may have missed a step. Actually, let me take a look at what ETH-tool says for this device. It did come up at 10G. That's correct. This is the 100G capable device, so yeah, that's right. I may have the wrong interface, perhaps. Well, this one's definitely correct, so I'll do TCP dump. dump-i. Yet again. Okay, that's... Well, I can try a couple of other things. Let's see. Maybe it's running on ETH1 instead of ETH0. Oh. Well, that might have something to do with it. Or maybe not. All right, so it is up. It's also possible I just have it plugged into the wrong port on something. Again, because this is not actually passing through the link state, we don't know which one of these the card might be using. I'm not seeing anything on the other side. P8EDR, let's see here. So that is assigned, okay. And it is assigned over here, right? Okay. Okay, that seems fine. All right, well, I need to do some more debugging here to figure out what's going on. But the driver did load, and it does talk to the NIC, so it's at least well on its way to working. And the 100D design is taking its time. Anyway, so I'm probably going to shut this down for now. It's going on, what? It's like 3:40 already. Yeah, so... Oh, send raw with escapee. Well, you should be seeing ARP requests or something. And I'm simply not seeing anything being received on either end of the link. So if you bring everything up and you assign addresses, you should be seeing traffic one way or the other. All of this stuff, as far as I can tell, is local traffic. Yeah, which is yeah, which doesn't help, because if we're not receiving anything on either end, then something is not working. I've had issues where the link works in one direction but not in the other direction, which is annoying. Actually, one thing I can try real quick before giving up on this completely is just resetting the NIC. Let's see. Modules. That will reset the NIC. Okay. Let's see now. IP link. Okay. We'll go ahead and set that up. Right. And then I will assign an IP address again. Yeah. Not working. Well, I guess I can try the other one real quick. So set ETH1 up. It's possible I just have a wrong idea about which interface is which on the card. So I will transfer that over there and try. Oh, okay. Hey, there we go. It works. Nice. I plugged it into the wrong plug on the card, apparently. I'll have to figure out where that crisscross happened. But there you go. We have traffic flowing through the NIC. Let's do a test with iperf then. Let's see, iperf 3-S here. iperf 3-C. And we're going at, well, not quite 10 gigabits a second. I have noticed that these AMD CPUs are not quite as performant as the Intel CPUs. I don't know why. Let me try running with a few threads. 9.38, 9.3. Okay, that's what we expect. For 1500 byte frames, we expect to see 9.42 gigabits per second. So there we go. We have line rate operation at 10G. 100G design is not done yet. It's still running. So yeah, there you go. I'll probably be. I have some stuff I need to clean up, obviously, but I will be getting this this code up into the repository. I don't know, probably in the next week or two, and then the U280 will work out of the box. And the next step is to get the JTAG cable for the U50. I'm not sure if I'm going to wait for the one from Xilinx or if I'm going to reverse engineer this this connector. Maybe both. All right. Well, I think that's about all I got for today. I hope you guys found that interesting. Hopefully you guys learned a little bit about this sort of thing. If you have any other questions, I can hang around for a few minutes if you guys want to ask. If you want to see anything in particular. If not, then I'll probably sign off in a couple minutes here. Actually take a quick look at the manual to see if it was documented which transceiver was the correct one. Not seeing anything about that. Interesting. Let's also see which documentation was correct and which documentation was wrong. Let's see, I pulled those pins. Which way did I pull those pins? I pulled those pins high. I pulled FS high, and what did the XDC file from Xilinx say? The XDC file said... Oh, the XDC file was wrong. XDC file says you pull it to 0 for 161. Well, go figure. This thing is full of typos anyway. The test bench for the AXI Lite stuff. Well, you mean AXI Lite period or AXI Lite in Corundum? I could pull up my AXI library and show you some pieces of that. I guess I can pull up my AXI library real quick and show you how that works just briefly in Python. I might not have it open. I might need to go hunt that down. Yeah, I need to go hunt that down. Let's see. Hang on a second. Open project. Let's see. Verilog, AXI. All right. So AXI Lite stuff. Well, all right. The model, the simulation models for AXI are a little bit complicated, but that's all in the Verilog AXI repository. Yeah, more general the better. Okay, so let's see. So yeah, so in my Verilog AXI repository, I don't know if you looked around at this stuff at all, but this one has both the AXI models and the AXI Lite models, as well as a bunch of, interconnecting IP. So this particular file has the simulation models for AXI Lite. And the way it's set up is maybe, I don't know, it's perhaps a little bit different from how people do this stuff in just pure Verilog. The idea is that this model uses internal queues to handle the read and write requests. So the main functions that you use are init read and init write. And these, they simply place a command, which is just, the corresponding arguments into this queue. And then there's this create logic call, and I'll show you how this is used in a minute. This one is what you actually connect the signals to, and this one actually forms the bus model. So this write logic is on the right side. Write response logic is handling the B channel, address interface, data interface, and, oh, actually, hang on a second. Okay. How does this work again? It's been a while since I looked at this. So write logic. Okay, these don't actually talk to any of the signals directly. When you initiate, say, a write, this code runs and generates the internal bus cycles. So the thing is, when you issue a read or write operation by calling init read or init write, you don't have to write a single word. You can read or write an entire block, right? Which could be, hundreds or thousands of bytes or something like that. So the read and write logic, or sorry, the write logic and the write response logic will say, take a write request that you've initiated, and it will split it up into individual read and write operations over AXI Lite. So if you want to say write 256 bytes, well, you can't issue a single AXI Lite operation for that. You have to issue, what, 64 smaller operations for each for 4 bytes, if it's a 32-bit interface, which, I mean, ARM specifies that it's always 32 bits, but, you know, it's not too hard to make a 64-bit or something AXI Lite interface. So anyway, that's what this does, and it puts all of those in a set of internal queues. This is for the write address queue and for the data queue. And then we have the interface logic that takes stuff out of these queues and actually issues those transfers over the internal AXI bus. So this is super simple. It gets a what's the write response logic? Sorry, we'll take the address interface logic. What it does is on every clock edge, it tries to pull something out of the write address queue, which would contain the write address. I don't think there's anything else. I think that's the only signal. Then it will set that, and then it'll wait until it sees AW ready go high, indicating that that's getting clocked out and consumed by the device on the other end of the connection. And then it will repeat that for every operation. The read, so write is basically one way. You can initiate a bunch of writes and that's it. For reads, what you'll do is you'll initiate a read, and then the read data will show up in a queue where you can pull it back out. So the read logic does the same thing as the write logic, where it splits up a big block read into a bunch of individual reads. And then the read response logic takes the read response data, packs that up into a block, and then puts that into the read data queue. So we can look at a test bench for this. Let's see. I guess I can take a look at what do we got here? Maybe the AXI Lite, the AXI Lite interconnect module. So yeah, this has a bunch of code here because there's just a bunch of ports that need to be connected. But the way you use it is very simple. You can issue, let's see, this is issuing a write. So we do AXI Lite master.init write. You give it the address, which is in this case is 4, and the test data, which is 11223344. And then the model takes care of the rest, and you just call wait. So if I run this, it's a AXIL interconnect 4x4.py. Right, that'll run and do its thing, but I'll do GTK wave interconnect 4x4.lxt. Okay. All right, let's take a look at this here. I go to, well, I guess this has everything in it, doesn't it? Okay, so I can zoom in here, and this is the first operation that's performed. Let's see. I have to look at the slave interface side. AXIL AW valid. So the first thing that we're doing, right, is this is a write of 11223344, right? So we call init write, and let's see here, AW address that gets set to 4, and let's see, where is no, that's not it's W data. There we go. Here we go. 11223344 on the first of the 4 interfaces. These are 4 interfaces that are concatenated together. But anyway, there you go. So that shows up, and then that would get clocked through, and it'll show up on the other end. So we've got the 4 strobe bits. There's the actual data. That'll get clocked in, and then the response channel will come back. Here's the B channel that comes out. Okay. And then, reading, same kind of thing. You say, okay. Well, so what happens after this? This goes all the way through, and then it hits the RAM model, which is not actually in Verilog. That's also another Python model, and that will handle the writes and actually update its internal state. Let's see. Yeah, so that'll take place, and then this will read that out and check it. So it wrote it at address 4. calls read mem to read what's in the internal state and asserts that that equals the test data that we wrote. And the same thing in the other direction. So that's basically how the model works. Now, if you haven't used AXI or AXI Lite before, it's divided up into several channels. You have, let's see, let me go to a simpler file here. I guess I have an AXI Lite. Do I have an AXI Lite register module? I do, okay. So it's divided up into several channels in parallel. Each channel acts like kind of like AXI stream, where you have a ready and valid handshaking. So three of the channels are used for writes and 2 of them are used for reads. And the reason they use 3 for writes is just because it's a subset of AXI, and AXI uses 3 for writes, even though you can probably simplify it and remove and combine these 2 of these channels. So the first channel carries the address information. So when you want to perform an operation, you would put the address you want to write to, for example, on this channel, and then you would put the data onto the W channel. So AW channel is the write address, W channel is the write data, and then the B channel is the response that comes back. And all of this is done in FIFO order. So if you issue 3 requests on the AW channel, then you also have to issue 3 requests in the same order on the W data channel. It's possible to at least try to initiate something on W data first before AW, but usually the device at the other end will block and wait until it receives the address. Once the operation is complete, then you get a response. And this is, well, it's useful for 2 reasons. One of them is that an interconnect module can complain if you're trying to access a slave module on the other side that you're not allowed to talk to. Or if the address decode failed, you're just trying to access an invalid address or something like that. That allows you to get feedback. With PCI Express, at least from a software standpoint, well, what happens? I guess if you do send something to an invalid address, you'll usually get a packet back. So yeah. I want to say for something like Wishbone, I don't think there's any sort of response channel in this way. Anyway, so it does that, and then it also allows you to ensure ordering, right? If you need to ensure that a certain write has taken place, then you can wait for the corresponding response to come back. And then in the read channel, it's basically the same thing, except we have just 1 channel in each direction. So that's one thing I need to make clear here, is that the AW and the W channel are both going in the same direction, and then the B channel comes back. In the read channel, it's the same thing, whereas the AR channel goes in one direction, and then the response channel, the R channel, it comes back. So same idea here. You will send an address on the AR channel, and then you will get the data coming back on the R channel later. So it's a relatively simple interface. It's a simplification of AXI, whereas AXI has the exact same signals, but it allows you to perform basically burst reads and burst writes. So if I want to read, 100 bytes from something, then you can issue a read over, AR ADDR, and you can set the length to, however many bytes that you want. Obviously, it takes more logic to actually implement this, and it's more complicated. So that's where AXI Lite comes in. If you don't need that kind of support, then it simplifies stuff quite a bit. So in Corundum, we use AXI Lite for register operations, so the driver can access configuration information on the NIC, but it's not particularly high performance because you can't move around big blocks of data. If you're doing block operations, then you need something a little bit better. So actually, I will say that with Corundum, initially we used AXI internally to interconnect all the parts, but we ended up running into some very serious performance issues as a result of using AXI. And mostly this came from arbitration logic inside of all of the AXI interconnect components. And basically we sat down and we're like, well, we could maybe do a huge amount of work in the interconnect logic to try to remove some of these cycles, but it's unclear how much we'd actually be able to do with regards to that. And there's some other performance issues associated with the DMA cores and the data realignment that needs to take place. And that requires the use of additional clock cycles. So what I ended up doing with Corundum is writing a completely new custom interface protocol that's used internally that I based off AXI Lite. So it doesn't support any bursts or anything like that, but it does. But it offers the capability for much higher performance because the arbitration logic is much simpler. We're not doing any address decoding. We use a sideband signal for determining how stuff gets routed. And it's also a segmented interface, which means that we can play some interesting tricks with accessing things. Let me actually just show you what that looks like really quick. It's kind of interesting. Let's see, where's the best thing I have to look at this? I guess I can take a look at the PCIe DMA cores that use this. Oh, not the AXI DMA. DMA IF PCIe US. Okay, here we go. So this is the segmented interface that we use. And you can see it is somewhat similar to AXI Lite, where we have a, well, in the right direction, we only have one channel, which is just the write command. So we get rid of the response channel, and we combine the address and data in the same interface. So you don't need to worry with, binding these together in some way. And then in the read direction, it looks basically the same. We have the address going one way and the data going the other way, and that's it. But we also have this seg count parameter, and we also have this select line. So these are a couple of the main changes that we made. This select line supersedes using the address to select what device you want to talk to. So that means we don't need to worry about, how many address bits are we going to use for this device, how many address bits are we going to use for that device. We just use the select line, and we can make it wider or narrower as we need, as stuff progresses through the hierarchy, and that makes it much easier to parameterize the design. And we don't need to assign addresses, it's just based on how the select line is set. And then the second thing is using segments. And what we do is, if we have two segments, what we do is we put all of the, say, odd addresses on one segment and all the even addresses on the other segment. So if you use both segments at the same time, you can access two adjacent locations in memory. And that means that we can source or sync the TLPs to PCI Express at full bandwidth without any penalty over the bus. Because with AXI, as soon as you want to do a shift one way or the other to get things aligned, you have to start inserting extra cycles. So yeah, it was a little bit of a pain to have to implement this this segmented bus, but without doing this, we wouldn't be able to get anywhere near line rate. It'd actually be interesting to see what the Xilinx XDMA core is capable of, because for Corundum, I actually had to write my own DMA engine. I mean, that's what this is right here. When you want to talk about some annoying Verilog, yeah, that's 1,500 lines right there for the read direction, and about 1,200 lines or 1,300 lines for the write direction. So yeah, this is one of the more complicated parts of Corundum to get everything working. Well, the other thing that we were able to simplify a bit is, since we're not doing any address decoding, we don't need to worry about any page boundaries. So with AXI, there's a limitation that any burst operations that you do cannot cross a 4K boundary, because that could address a different device or something along those lines. So with this segment interface, one, we're not doing bursts, so that's not an issue. But we don't need to worry about this 4K boundary crossing at all. So we don't need to figure out, okay, are we crossing a 4K boundary or not? And if so, where do we need to cut the read or the write operation to respect that 4K boundary? So yeah, that actually resulted in a pretty significant savings in logic resources. Even though we're going to double the interface width, we can save some logic resources and we can save some timing performance and get a little bit more slack to play with. So yeah. Anybody else have any other questions about anything? Otherwise, I'm probably going to sign off soon. I've been streaming for like, what, 3 hours now. Also, I guess one thing that I should mention about some of the Xilinx IP is that, at least as far as AXI stuff is concerned, they're somewhat notorious for having buggy IP. I know, but I think Dan from Gisselquist Technologies or whatever, who really likes doing all of the formal verification stuff, he's run into issues with that before. So, yeah, for me, since I'm using the open source Icarus Verilog simulator, I try to avoid using as much Xilinx IP internally as much as possible, because I just can't simulate it. At least unless I totally rewrite my entire framework. I'm thinking about maybe moving over to using, what's the name of that program? There's another Python-based framework that can be used for co-simulating stuff. CocoTB. There we go. And that one will work with many simulators. So, but yeah, migrating to that now is a little bit of a tall order because, well, let's just say that's the PCI Express simulation model. You thought the AXI Lite model was long. Yeah, that's 4,500 lines for PCI Express. So moving that whole thing over to CocoTB or something, while it would be an interesting project, would be a lot of work. And I'm not even sure if CocoTB supports the functionality required to implement this. Okay, nobody's got any questions or recommendations or anything? All right, well, I think I might just wrap up this stream then. Thanks to everybody for listening in, and hopefully I'll be able to do this again sometime soon. We'll see.